All right, pull requests this week. I did not see a whole lot at all. Um, there was one new pull request that looks really interesting from Radic. This is introducing huge page-based read buffers. So if you're interested in that, it looks interesting. I'm not sure under what circumstances this is going to end up helping, but it definitely could. So, um, yeah, there's this one. Otherwise, I didn't see anything new or closed. Besides that, there are a couple that got updated this week, though. Adam's retry of BlueFS fine grain locking. This went through some QA this week, and it was passing cases that previously apparently failed. I don't know if that means this is ready to merge yet, or if we still need to run this through more tests. Certainly, that code is complicated, so this is a touchy one, and it's unfortunately it's also kind of this is Adam's attempt to fix what was wrong in a previous PR from Majian Peng that also we merged that also broke master. So right now we're 0 for 2. Maybe hopefully on the third try we'll get it, but this is tricky code to get right. All right, let's see. Beast optimizations for request timeout. I love this PR. There's tons of benchmarking data in it, lots of discussion about what makes sense to include or what doesn't. I know, Casey, you've been reviewing this. Anything else you want to add?
Since last time, let's see, we got a comparison with and without the custom allocator piece, which was kind of complicated, and we found that it didn't really help. So I was happy to rip that piece out. Mark is satisfied with the performance, so I ran it through Toothology and see some Valgrind issues that are there. So we talked about it in the bug scrub this morning. We have a plan for that.
Cool. Yeah, it looks great. I mean, definitely looks like an improvement. So that's fantastic.
Yeah, the piece of the Beast library that we were relying on for the timeouts is kind of complicated and doing extra stuff. So getting rid of that, I think, is the main thing.
Okay. Excellent. Do you know there was another PR that was kind of hurting RGW performance? It looked like I need to go back and look at which one it was, but are you
Yeah.
guys looking at that too?
Not really. So the PR was so the Beast front end is spawning coroutines for each request, and
Yeah.
and there's a stack allocator for the coroutine stacks. And originally it was just using memory from the heap, and it was sized pretty small, so we were seeing a lot of Valgrind issues just overrunning the stack. So that PR switched the allocator to use mmap and mprotect so that we would actually crash if we overran the stack. And so, I mean, that adds a couple of system calls for every request, so we kind of expected a performance hit there. So I don't think that we're planning to revert that, but maybe there's something else we could do.
Sure.
But I think that this timeout thing was the much bigger issue.
Okay. Well, cool. Excellent. Sounds great. All right, let's see. Next, there's this PR to set the min alloc size to the optimal IO size for the underlying device. There's some discussion. Eventually, both that was approved by both Sage and Igor. So I believe now it's ready for testing. There's also this PR from Igor to make shared blob FSCK much less RAM greedy. that needed a rebase. It's gotten an update since then from Igor, but I'm not sure if he did anything besides just rebase on master. So I think that one may be ready for review and testing. And another one from Igor. This is this old PR for optimizing PG removal. It's been under lots of review. There were some failures, testing, more review and discussion. I'm not without Igor here. I'm not sure what the status of that is yet. But anyways, it's still being actively worked on, so that's good. Lots of stuff in the no movement category this week. I know I've got a couple that are in there, but I just haven't been touching them. My big one, I guess, is this priority cache. It was more or less working in performance tests. Well, it was working in performance tests, just not showing a whole lot of improvement, really. But then it segfaulted during testing, and I haven't gotten back to it yet. There are some benefits to it, just not what I was hoping there would be. So it's still probably worth doing. Just it's not a big improvement. It's a much more nuanced, minor kind of thing. But it does give us a lot of insight into what the cache is doing. So maybe that's the big win. Otherwise, we still have the Mds optimizations here, which I think are really can be good to get in. But Patrick, do you know, is anyone still looking at those, the ones from ukernel?
No, not yet. I'm
Sure.
hoping to look at that in the next few weeks.
For kind of interestingly, I've gotten a lot of people recently asking about like HPC and IO 500 with CephFS. So there does seem to be a lot of interest, at least tangentially, right?
Yeah. Well, we'll see. I'm not sure if the approach is right. Something we want to support long term. So,
Yeah.
Hard to say whether or not those will actually get in.
Okay. All right. Well, let's see. Yeah. I mean, there kind of likewise on this optimized object memory allocations using pools. Ronan you're Ronan here. You had raised some issues about that PR, and I think they're very legitimate. So that's another kind of question of it could be a big performance win doing something like this, but we have to figure out the right way to do it. I don't think we saw a response back from the author of that PR, so still kind of waiting on that. All right. Well, otherwise, I think that's about it for PRs. Anything I missed or anything anyone would like to discuss? All right, then moving on. Okay, so first thing this week I wanted to bring up is that there's been a lot of discussion, mostly inside Red Hat, regarding how long it takes to build packages. Building Ceph itself is actually not horribly slow if you have enough cores. On our really fast development machines, we can build Ceph in probably about 10 to 12 minutes, which is not great, but it's okay. But our debug or our actual package builds take a lot longer, and there's interest in trying to figure out why. So the two big things that came up, was interest in trying to parallelize builds across multiple nodes, and David Galloway has been doing a lot of testing on that. Right now, he's trying. It's some kind of closed source tool. I forget the name of it, but the gist of it is that it's faster, but maybe not as fast as. It uses a lot of nodes or a lot of cores to get an improvement. And DistCC may kind of be similar in terms of this improvement, so he's testing that as well. But the other big one that I wanted to bring up this week for people is that Sage had mentioned that he saw a lot of time spent in DWZ, which is basically a tool that lets you extract symbols from packages or from the code to build debug packages. So it looks like, from what Sage had said, that that's basically single-threaded. We're spending a lot of time in one core during package build, just doing that step. So I haven't looked at it really closely, but I posted the link for the DWZ source code in the Etherpad. It's basically a C program. It is being actively maintained. There appears to be someone at Red Hat that's working on this, but perhaps this is something that could be parallelized. I wanted to open it up for anyone that is interested in this. Has anyone used DWZ, knows much about it? Looked at it at all? All right, that was somewhat the response I expected. Okay, I've looked at this just a little bit now. I don't know how difficult it would be to actually do anything with this. I haven't looked at it closely enough to really get a sense of it. There is some comments right at the top of the C source talking about trying to optimize multi-file cases. So, the author definitely has been thinking about things, performance at least a little bit. I may try to reach out to him and see if there's any opportunities for us to help. But in any event, I think that's probably the better way to go in terms of trying to make our package builds faster, at least at first, rather than trying to parallelize and use multiple nodes. And we already can make the parallel parts fairly fast just by using a big node with lots of cores. It seems like the single-threaded parts are the ones that really are hurting us right now. So anyway, that's it for that. All right, next here, Josh and Gabby, do you want to continue? Maybe quick summarize the discussion from core this morning about fast shutdown.
I can start my part. So with no column B, we require a step before shutdown, a step where you stage all the allocation table, and that step must be done when the system is fully quiescent. If there's anything happening, if there's compaction ongoing, if there is still ongoing writes, then this thing would be bogus, and next time we start, it's going to be bad. So there are two solutions. The first solution is just, if you do fast shutdown, then don't store the allocation file, and the next time you start, you will do a full restore, a full recovery. Full recovery can take minutes. If the system is very big, it can take 15-20 minutes. I believe that you should expect 5 to 10 minutes on every reasonable system, but it could get as much as 20 minutes on a fully configured system. That's one solution. A better solution is on fast shutdown, try to do minimal set of operation to get the system into quiescent state, and then stage the allocation and shut down. The step we could skip are all the cleanup we do for memory and stuff that we don't really need. Like you don't need to drain memory pool, you don't need to, free up all the memory and let malloc and new and free deal with all the fragmentation. You can just skip that step. And so I've been working on this for some time now, and today I start profiling the step to see how much I'm saving. And I was very disappointed to see on my system that with the minimal setup operation, I can go down to like 1 second. And if everything is done, it's going to be 10 seconds. So I know it sounds like it's a factor of 10, but it's just 9 seconds. And still, when I do this 1 second and I think I'm in good shape, but still I'm skipping a lot of step, which I might be missing something. The question is, why do we do the fast shutdown? My intuition is that we don't do it because we try to save the shutdown time. I don't think it's very long. I suspect people need fast shutdown in case some bug put us on deadlock or some kind of a condition preventing the system from ever going to shut down. So it's just, okay, kill the system. But it's it's something I suspect. I have no knowledge about that being the case. My question to people is, how much time do we spend on shutdown if the system is in good shape?
So I don't know about the second part, but I can tell you about the history of why this was implemented. It's actually a fairly recent addition, only in the last few years that we had the fast shutdown. And it was implemented in order to make upgrades in particular go faster on large clusters when there's heavy IO load going on. So when you're having to restart each daemon across the entire cluster, you want that to happen pretty quickly so that they get back up and running and continue serving requests. I think one of the aspects that you may not be seeing as well in your testing on the Optimizations like NAS nodes, because they're so fast and have these very fast NVMe devices, is the flushing of data in flight is going to be pretty fast in those nodes, which wouldn't be the case if you had slower hardware like a hard disk or a much lower CPU. I think that may be one aspect why we'd see longer shutdown times in some cases. But that's not to say that we have to do fast shutdown or we have to. I think it is worth trying to like figure out where the time is actually being spent and what is worth optimizing and not.
So there is
Josh,
one step.
case of.
Sorry.
I just
wanted to add to.
Go ahead.
Hey, thanks. I just wanted to add the use case too. If a site, for instance, is wanting to shut down for an outage, let's say they have 100,000 OSDs and then 1 or 2% of them are slow, that could completely halt their whole plan, where they could be governmental, could be financial, losing tons of money waiting for this node to shut down. So there could be a big difference of what a fast shutdown could do. And being newer, I still don't know all the details of it and what we're looking to achieve, but there could be a case where something just never shuts down because hard drives like to still be operational but be very finicky, especially the more commodity type hard drives. So I just wanted to add that.
So it's another, there is another solution that we discussed, which was do the shutdown, but cap it at 5 minutes, 10 minutes. If you cannot do it in 5 minutes, then kill the machine, and then you will do a full recovery afterwards. But the full recovery should probably not take you more than 10 minutes, so there's no reason to wait 10 minutes to save another 10 minutes. So you should never wait 1 hour or 2 hours. But if we could, maybe it's enough just to do this thing. Plus, there are a few other simple changes which don't change the semantic. There is anything which is not starting the execution, but it's in the queues. So when the system is slowing down, I expect a lot of stuff is being queued on the external queues, but we didn't start executing them. So something that I'm already doing in this solution is I'm stopping all the queues from accepting new tasks, the external and the internal. So nobody is going to start anything. only the stuff which already start execution is going to complete. The question is, how many tasks can we have in flight? Nobody knows. We must have some limit for the in-flight stuff.
That's another area where I think we've made a recent change there. For a long time, we actually had no limit, and so we could have very, very large buffers of data that was incoming to the OSD. And we finally enabled that again. It's the OSD message cap limit, which is what did we set that to? Like 100 or something? 1,000?
256.
So that means we have as much as 256 messages that we're processing.
When you say message processing, mean external, we got 256 external messages being processed on the OSD at one time.
Right.
That's not too much. I mean, even if we assume that every IO take 10, 20 milliseconds, you could still finish just the IO in I would say 5 seconds. Like the slowest SATA drive would finish the IO itself in 5 seconds. Then there is the processing that we do, make it to be 10 seconds. So that's not where we spend time. I don't think this is where we spend time. I suspect that there's some cases that, so one thing would be maybe the queues got thousands of pending IOs that we didn't start executing, which we still keep bringing in. That thing is easy to stop, and I'm already doing that. I'm not going to add anything new to the execution, but 256 IOs, that's not something that would cause us to wait minutes. Like 1 minute should be enough to complete everything and with huge margins.
The 256 IO limit happened after fast shutdown was implemented though, right, Josh?
Yeah, so that could have been that we were just seeing the effects of not having a limit more than anything else.
So maybe that was the reason that people, so that fast shutdown was needed if there was no limit. And by the way, even today, there is still similar thing because you could have things queued before they start executing. I don't know how much we can have in that queue. The message queue on the OSD, everything arriving from the clients. Is the limit to how much we could queue?
Yeah, that's what we're talking about, the message limit.
So talking about execution queue or pending execution queue?
The pending execution queue, the messages coming in off the wire from the client. That's what's capped at 56.
Oh, so we kept it just on the pending, but not on the executing? That's actually the best thing to do. Because I would expect that pending don't consume a lot of resources while executing do consume resources. So I would put a much lower cap on execution and bigger cap on pending, because pending is just the reason is that there is solicited data, so that the host can send the whole data together with the request. That's why we must put a cap.
Yeah, so you may have like each request being 4 megabytes of writes, and it's taking up a whole bunch of memory.
Okay, so even without any of my changes, there is only 256 possible IOs, which should be able to complete in few seconds. Plus, there is cleanup that we do. Assuming that there is no bug and there is nothing stopping us, then I would expect that 1 minute should be more than enough for any system.
Josh, do you remember, did anyone, when fast shutdown was implemented, actually look at why it was needed or where time was being spent?
That's the BZ I just pasted here. So that's where the context comes from. It was coming from Rook, if I remember correctly. And I also found, I am sure Gabby has already looked at it, but this is the pull request from Sage where this was implemented.
That's the...
So upgrades, as Josh pointed out, was the reason. And like 25 to 30 seconds per OSD was not acceptable, is what I'm understanding just by reading through the initial comments.
We avoid the complex clean shutdown process, which is historically a source of bugs. That's not confidence inspiring.
Yeah, but I guess with Gabby's stuff, some of the details in this PR don't hold, right? I mean, like the only reason why we are doing clean shutdown now, we'll have more motivation, right? We have other stuff to do during shutdown. So it might be worth revisiting whether we can afford to have a clean shutdown, given that we have the client cap message size cap.
Do we have a system we could try slow system, big and slow? I need something big and slow.
Long running cluster is large and slow. It's almost all HGG.
Do you need it to run your code, Gabby? Then
No, I want to see not fast shutdown with system doing I/O in full capacity, and I want to see how long it takes. Because if we can see that takes, I don't know, 5 minutes at worst case scenario, I don't even think that be the case. I think 1 minute should suffice to any reasonable system. Then I don't think there's much to gain on the fast shutdown, and we only risk creating inconsistencies.
I think that should be doable. It's just a matter, like we have long running cluster. We also have scale clusters, and this it's just a matter of disabling fast shutdown.
Okay. And actually, I think at the moment, fast shutdown is disabled in Ceph.conf. It's something other than
Again, I think we talked about this in stand-up. It's just disabled in vstart. By default, it is enabled. If you see options.cc or the new file name, it is enabled. Yeah.
My system, it's always disabled.
Because you're running vstart, right?
Yes.
But vstart uses a separate configuration file.
Oh, okay. Okay, so try to see the time. And as I said in the beginning, a very simple solution to this is to perform the full shutdown and just put a timer. If it doesn't complete within, I don't know how many minutes, 1, 2, 3, 4, 5, then kill the machine. So in worst case scenario, we could still do the full recovery. Full recovery on a big system is 10 to 20 minutes. There is never a reason to wait 20 minutes for shutdown. And if we think that few minutes should be enough to get a proper shutdown, then there's nothing to optimize. The code on my system seems to be working fine. I keep running and killing the machines and running FSK, and it gets fine, but I can always find that there is something I missed, some transient data which I didn't capture, and that's what scares me, because it's really hard to prove that this thing is really working.
I think we do have to be a little bit concerned, even if it's a minor increase for OSD, because when you're trying to restart like an entire cluster, and during an upgrade scenario, you're keeping things online, you're serializing things a bit so that you don't disrupt activities. So you're going like node by node, maybe restarting a few OSDs at a time, so you don't make the entire cluster unavailable. So in that kind of scenario, it does add up when you have add that sequential delay. So even if it's like relatively fast, I think it might still be worth optimizing. But I agree we should check out how much time it actually does take on something like the LRC, and if it's like only 1 second or something there, then it's probably not worth looking at. But if it is like a difference of 10 seconds, 20 seconds, then that is more significant and adds up over a large cluster.
So what I've seen on the official analysis was 10 seconds without the optimization, and about 1 point some seconds with the optimizations.
Mm-hmm.
But as you said, official analysis is a very fast machine.
Was that one OSD, Gabby?
No, FreeHOST.
Okay.
But you know what? Now I think about it. I think the IOs were. I was using random write. It might have been small. Let me see the size of the random write. Uh, 4 to 64 kilobyte of writes. So maybe if there would be megabyte, like 8 megabyte, if each write would be 8 megabyte, maybe it would be slower. So maybe I should also test with a very big write.
Yeah, that would be the worst case scenario. Giant writes late. And yeah, Chris has a good
Because
point
we
about
allow
other kinds of scenarios
256,
where you care about the whole
right?
cluster too, like shutting it down entirely. At least in that case, it can be done in parallel, so the extra time isn't so bad. It's really the long tail that you're worried about there. But the time and idea can kind of fix that case. Make sure that there's a maximum.
So what size, what's the maximum size that we allow the host to write to us unsolicited?
Typically, it's 4 megabytes.
But is there
In theory,
anything
there's
stopping the
larger.
host from doing 1 gigabyte of write without asking us?
Yeah, there is a hard limit on there's an upper bound on a single operation size. I forget what that's currently set to. Might be like 64 megs, 128 megs.
So doing 256 IO of 256 meg each, that would probably stress the system to its limit.
Yeah, certainly.
And okay, I don't know if FIO could do that much actually, because I think it have to keep everything in its buffers, or doesn't it? Because if it needs to do write followed by read, oh, but maybe they don't. I don't know if they keep any of the data or if they just throw it away.
I'm not sure either. Or it might even be using the same data depending on how you configure it.
In SCSI and Vimy, typically the initiator keeps the write data until you get acknowledged from the host, from the server.
Yeah, that's
I don't know
definitely
how
true within
Bluefs
the
does.
client-side library, the RBD, regardless of what FIO is doing.
So librd is sending the ACK immediately to the host, or does it wait for the host for the ACK from the server?
It'll still have it in memory so that it can resend if it needs to until it gets the ACK back from the server.
So probably I cannot use one client to do that much of an IO.
Yeah, but in practice, it's going to be a much lower limit. Like 4 megabytes is going to be the usual worst case. Maybe 32 for more aggressive setups, but that's pretty rare.
I mean, because even 4 megabyte, if I do 256 of them, it means 1 gigabyte of cache on the client side. But the client is able to do that much?
You might start hitting some throttles at different layers.
Yeah, so
Yeah,
that's why
you could run multiple clients more easily, probably.
yeah, so I probably need multiple clients. I don't think one client could do that much.
Mm-hmm.
Mark, could you please help me running the setup? Or we could do it afterwards, or when you have the time. How to set up multiple clients to do big size I/O and using a slow machine.
Slow machine, the difficult part. We have the insertive nodes, which have hard drives. But
so I need an insert node.
yeah, but they're four of them are being used by the Jenkins, and the other ones I think are mostly checked out. Those might be tough. We have the ancient mirror machines, Josh. They're very slow.
Those are incredibly slow. That'd be a good worst case. You can find one that works.
Yeah, so Gabby, that might actually be if you want worst case scenario, that would probably be the worst case scenario, is grabbing one of the mirror machines. So those are Toothology or in the standard lab, so you'll need to check one out. using that. I don't know if you...
Send me the names. And for running multiple FIO, can you just keep opening more and more FIOs? And is there any synchronization happening between them? Can they all write to the same OSD?
Sorry, what was the question, Gabby?
Can I open multiple FIO on the same host?
Yeah, absolutely. You can run multiple jobs from one FIO. You can just run multiple independent FIOs. Pop up the queue depth for each one. So for each one, you'll want, if you want to have a high IO depth for each FIO process, you'll use libIO and direct and pump the queue depth up and just do like large writes, whatever you want to set it to. So yeah, I mean that'd probably be the way to go, I would think. And you'll probably melt the mirror machine because I mean these things are like 10 years old, so they'll be it's gonna be super slow probably, but you'll learn something maybe.
Yeah, because also for now, one thing I notice is that that the stage part is not what is spending the time. Most of the time I'm spending, or the stuff I'm skipping, is just inter-cluster synchronizations. It's not an IO. It's like getting everybody to agree on some steps and stuff like that. Talking to the manager, talking to all other components. But I don't see the IO itself as something taking too much of my time. Sorry, I'm saying before I try to optimize. When I optimize, that's the only thing left. But the 9 second out of 10, they're all been some kind of synchronization happening. Like a very big chunk was even spent inside service prepare to stop, which is essentially a communication with managers and others. I think we spend half of the time just here.
Yeah, I'm curious what that will look like on Mira because Mira has everything slower disks, slower CPUs. It'll be interesting to see how that time spent changes. Josh, do you know how many of those machines do we have left?
Maybe 50, and I'm not sure how many of those actually work still. So
I'm trying to think. Yeah, who the right person is to talk to about getting those. I mean, if David, maybe, I don't know if he still deals with the hardware there or not. Like you said, maybe just to randomly try to grab some.
Yeah, you might just have to randomly try to grab a few, and if they don't work, mark them down and keep going.
Do we have any documentation on reserving nodes without running stuff through Teuthology? I forgot how to do it. I haven't done it in a long time.
Yeah, it's in the Teuthology docs. There's a Teuthology lock command you can use to do that. But you can see here, there's that's the general page, but trying to link to the Pulpito page about the mirror machines. There's a bunch of them that are free, so in theory, those ones that are free are still work.
So Gabby, you'd probably need to grab some and then however you want to run your tests, like set the cluster on your tests. I mean, Teuthology could do it, right? You could set the cluster that way, but otherwise, you could use vstart or you could use CBT once you grab the nodes. I used to do that sometimes.
So vstart is the one I'm using. It's easy for me.
Yeah. So yeah, just grab the nodes, run vstart. Well, compile Ceph or whatever you want to do.
See how long just the drain step would take. Because at the moment the drain step is not where we spend most of the time. At least not on Officinalis and not with small IO. I can try it on Officinalis with big IO. I mean, that's an easy thing to do. But I wonder how many IO can they get. So the things which are beneficial is to disable rogues DB, compaction, all kind of this stuff. So I try to disable also all kind of unnecessary activity, like the move the L column family, where we take all the small IO and try to stage them. So this stuff is really good weight. And do we even count them to the 256, or they could be? Is there a limit of how many small IO we could store in RocksDB?
There could be more like generated by activity 6 is just the message limit coming in from the client side. There could be more like IO operations internally generated from those client apps. If that's what you mean.
But the stuff that we store temporarily in RocksDB in column family L, or the small IO, are they counted towards 256, or it's their own counter?
It's a separate piece. I guess there would be only, like, you're talking about the PG log entries, right?
No, not the PG log entries. The small writes.
Talking about deferred
writes, sorry.
Yeah, that's separate. That's not counted in the same way. But for deferred writes, you don't necessarily have to do them during the shutdown process. You can play them on service.
I'm disabling them at the moment. Even so, I never see them being activated. So I think I'm disabling them, but I never saw anything happening on my machine. I don't know why.
Well, they're only used in specific circumstances, and I guess they're more commonly used.
Because I got an SSD.
Yeah, exactly.
You don't okay, that's why. Yeah, so I have the code to disable them, but I definitely need a machine with a spinning drive because the deferred write I don't see.
Mm-hmm.
That's something that should save us some time, and everything to do with compaction should be. Mark, please don't put it here. This thing is going to go away as soon as the meeting is over.
Oh, just copy and paste. Right?
Email.
Okay, I can even. I mean, there's nothing super interesting there. This is just if you want to use the RBD FIO engine. I mean, something like that, right? You want to just do big writes with maybe a high IO depth and whatever dataset size is.
Depth to be very big.
Yeah, and so you'll probably want to do like. So, okay, one of the reasons I put it in here, though, is because we should talk about this a little bit. With num jobs, if you increase that, what will end up happening is that you'll start out at the same offset on the image at the same time. So I don't typically like increasing the number of jobs with FIO for like sequential writes. If you did random writes, it wouldn't matter. So you could do that too. But with sequential writes, you probably want to hit different RBD images.
No, I prefer to do random write because that's the worst case scenario, right? Sequential.
Yeah. Okay, so then just change that.
Yeah. I try to exercise worst case scenario to be random write, big random write.
Yep. And then you can change, if you want to, you can just use more jobs then. Then it doesn't matter. Otherwise, you can run multiple FIO processes parallel against different RBD images. Or you could just make one RBD image and then do like, num jobs equals, I don't know, whatever you want to set it to. And then the IO depth per FIO process, whatever you want that to be set to. With the RBD engine, you don't have to worry about like using direct one and all the other garbage that goes along with that libio and everything. So yeah, I mean, something like that. Just change it to randwrite and then choose what you want for the other settings. I can send an email too. So, and I assume that you want to just use like lib RBD with FIO rather than going through the whole process of like, setting up kernel RBD and writing file system to the image and all that stuff.
That should be enough. I'm just wondering how much, what's going to be the limit on data buffers on the client side? Because when we move to 4 megabyte of IO, if we ask the client to keep very, very deep queue, eventually it's going to run out of memory space.
Okay, I sent an email with that in it. Yeah, I think that should be fine. Just using librd and big IOs, random, and then, however many jobs and however much IO depth you want to throw at it.
By the way,
I don't see the data.
Another question, unrelated. It's something which bothers me a long time ago. Why do we allow clients to do unsolicited write? I mean, it's okay if it's 4 kilobyte, maybe 64 kilobyte, but unsolicited of 4 megabytes, 64 megabyte, that's something which is frowned upon usually. You don't want the client taking your resources. I mean, if you look at a normal NVMe server, an NVMe drive, the way you deal with it is that you send a request and you say, I want to do a write, but you don't send the data. And then the drive would come to you and say, okay, give me your data. So as soon as you send a request, the client need to allocate, to have the buffers ready on each side, but it cannot move the data to the storage, to the target, unsolicited. That was always the case with SCSI, with NVMe, and before. I realized that there is an optimization. If you do small write, then you send the write and the data in one step, and you could save the round trip. Probably very good optimization for 4 kilobyte, but when your IO is getting into megabyte, that's become less of an optimization and more of a hassle for the storage system. Because what we do if the client is going to do 1 gigabyte, I assume we're going to ask him to give the data in intervals. So we could do the same if he's going to do 4 megabyte. Was there ever a discussion trying to set what's the correct size for the data that we allow?
I don't know if there's a good answer that I have for why things were designed the way they were back when they were written. This is pretty old, right, Josh? I mean, this is how it's worked forever.
Yeah, I think that's pretty much it's been that way that it was started. So I'm not sure exactly. I'm not sure if that was a consideration originally, or if we really thought about it in that way at any point. But that's just kind of how the protocol was originally created.
So the reason data servers don't allow you to give them unsolicited data is because it allows them to control the way they behave. They know how much resources they have, so usually they're going to allocate that much buffers, that many requests, and they can accept the request, but then they will move the data on their own good time when they have enough buffer free for the data, because usually the request itself is just 64 byte of the IO request block is usually 64 byte. I think SCSI, FCP, NVMe, that's how much they give you. And when you want to push the real data, you have to wait for the server to tell you, okay, you can give me now 64 kilobyte, you can give me 1 megabyte, but the server needs to tell you how much to give it. And that way the server is always in control of the resources, and it could use recycled buffer and so on and so forth. And I never heard about this being a performance limitation, because you could see people working in almost wire speed with this behavior. And again, even if there is, I can see that there is possible optimization for a very small write if it's 4 kilobyte around it. But when you do megabyte of write, there is never a reason for you to push data unsolicited and hammer on the server, which it might be doing other stuff, and you're just consuming space.
So I don't know all the details, but I remember hearing stories that early on, there were many iterations of the messenger, and there was a lot of like changes going into a lot of this stuff early on. I think at one point, like we had a messenger that was entirely based on MPI in the early days when it was still at like, kind of focused on being like a luster replacement for supercomputers. Josh, maybe you know more, but the impression I get is that there was kind of a lot of chaos around this stuff early on, and I don't know exactly how we ended up where we are now, but
yeah, I'm not that familiar with that really early history myself, the messenger layer. But it seems like, I mean, one of the things I imagine I might be that it's a little bit more difficult to like pre-register your intents and then execute on them in a system like Ceph where data can move around across nodes, and you don't necessarily know exactly where your request is going to be going until you get around to sending it. You could have some extra latency. I mean, it sounds like you're describing the system's able to maximize throughput, but it sounds like that doesn't that kind of protocol have some inherent latency to it as well?
But you could maximize throughput if it's a small IO, because then the overhead of the round trip is going to be big if it's just 4 kilobyte of data. If you're going to send 4 megabyte of data, then doing an extra round trip, it's no big deal, because I mean, even TCP is going to keep sending messages back and forth. You're not going to move 4 megabyte in one buffer. Internally, it's going to open windows, close them, and keep asking you to give them more data. So the overall saving, sorry, the relative improvement in 4 megabyte going to be, I don't think it's even going to give you 1% extra. If it's doing 4K, maybe you're going to get 10% extra response time. You could cut the response time by something. But 4 megabyte, I would expect that you wouldn't see a huge difference in response time. I would say single-digit percentage, not even.
I mean, it almost kind of sounds like you want the default behavior to be what you described, Gabby, with the ability to embed the data for if it's small in the original request, and say, hey, if you can, just take this and write it if it's 4K or smaller or something.
I'm really unfamiliar with anybody doing unsolicited data. I know it's like since beginning of time, it was always the privilege of the server to control the flow because they are doing more and they don't want few strong clients to kill them, and they don't even know if this client is in high priority or whatever. So they always refuse. It was never allowed to post data. Some people are trying to do it if the data is very small, you could piggyback and such things, but I never heard about anybody doing megabytes of piggybacking data. Because what's the round trip that we do for 4 kilobyte nowadays?
Yeah, I get your point. Like it could be like a few milliseconds for on regular TCP network, right?
Might even be less, depending. Some of them are pretty fast these days.
And that means that you could create an adversary which could kill your system by sending that much data. If we allow 32 megabyte, then I'm going to shut 256 requests each of 32 megabyte, and your system performance is going to suck.
I think from the traditional system, they were optimized to use the queues as they are fixed. And that's why you need to just ask for whether you could send something down or not. But the idea, I think, is not that bad. To have some boundary where we just don't allow to send the data straight away. And we could gain perhaps some decoupling from those really big data streams and have a better handling. Just get leverage or just at least improve also the things around QoS. So
Yeah.
So QoS is the big killer here. Because if you have somebody doing small I/O and is high priority, and somebody is doing these huge buffers, it's going to consume other resources.
And that's what we see, Gabby. It's legitimate. I mean, we have kind of fairly big QoS issues. Maybe this is something we should be thinking about more. I don't know how hard it would be to change, though.
I'm not sure exactly how big of an issue it is with, like, once you have mClock enabled as well, the mark. It does try to be able to handle that, but yeah, that doesn't mean that you end up having potentially more like system resources in terms of the queuing space used by these large requests potentially.
Yeah, exactly.
You're not going to service them immediately. What you'd usually do for big requests, you would put them on different queue, and you'd pull one of them every end request. If you want to do any kind of QoS, you could say, you know what, after I've done 100 of 4 kilobyte, I'm going to be willing to do one of your 1 megabyte requests, unless you set yourself to be top tier and I don't know, whatever. But it's unfair to have me doing 1 kilobyte and you doing 100 megabyte, and each of us get one entry in the queue.
Right.
And usually
mClock does account for that kind of difference.
Reps.
Yeah, mClock does account for that kind of difference, but I guess what it doesn't do is it doesn't stop you from taking up that queue space in the server in the first place. So I guess the difference with this kind of mechanism.
You only send the request, you don't send the data. We don't accept data up
Yeah.
to some limit.
I'm saying that's the advantage of that kind of system compared to what, just the mClock implementation that we have in Ceph today. Is that it does allow you to push back on that and control the buffer queuing space as well as the just the order of requests.
I would even suspect that once the OSD gets big requests, it will prioritize them because serving one big request free up a lot of resources. So you would even try and benefit the biggest offender. The more space they'll ask for, the higher the priority you would get because you want to get rid of them. I don't know if this is what we do, but that's
not what we do today. But that's
okay.
something that could be done, I guess. But that's not how mClock works.
Okay, so then it's good. It's good. I was just worried that something thing to, because usually when you have a lot of stuff, you try to get rid of the bigger one. But if there is no limit on how much they can push, if you do that for them, they will give you another one.
Yeah. I think this might be a good idea to investigate, and it's not just the client requests as well. It's also like the inter-OSD requests in some cases, like for recovery or for those kind of things can be quite large as well, or replication traffic too.
Another thing that we might be able to do is, if we do the request in the sequence of operation, actually probably we're not going to do that. Because you don't need to allocate the data buffers. You could just set up the request, update RocksDB, pglog, and everything, but then the data itself you'd accept in smaller chunks. Okay, give me 64K, you write it down, give me another 64K, you write it down. So everything is linked together. but you're not going to allocate very big buffers because it's. I don't know if this is what we do. If we allocate 4 megabyte of buffer, so it's sitting there idle until we get all the data, and only then we could start staging it. Which again, it's expensive. It's cheaper to take them in chunks, and each time you get something, you stage it. But then you need to build a mechanism that you know how to link stuff.
Yeah, I guess it gets into that kind of low-level messenger protocol, which is where it gets complicated to implement. Because today we do need to read in at least the header of the message before determining the payload size, and then we allocate a buffer for the whole payload. Then we read that in so that we can decode the payload. We do delay the decoding aspect of that, as we don't necessarily fetch that all immediately, but we do treat that as a single large buffer.
Yeah, so I'm just wondering if it's possible just to decode the header, do all the work that it needs to be done, and then start. Then you need to have an active thread pulling the data and staging them in chunk, but you don't need all the buffers. Just you could do double buffering of 64 kilobyte and just get the whole data instead of getting a big 1 megabyte. I don't know what happens if you do. Somebody gives you 128 megabyte. Are you going to allocate 128 megabyte of space?
Yeah.
And then, so this thing is going to be sitting idle for a very long time because until this thing is complete, then this thing cannot be touched. And it's not a very good usage of resources. Resources going to be sitting idle most of the time, just waiting for anything to happen while you could start staging things. So in effect, you're actually slowing them down. So I would even suspect that doing a multiple 64K loops would be faster than giving you unsolicited 1 megabyte or whatever.
Well, how would the multiple 64K loops work when you need to write down the entire write as a single update to the disk? Because I think you're sending that off to the object store as a single transaction.
It should be a single transaction. You're going to start a transaction, but you don't mark it as completed until all the whole data is safely on drive. I mean, you first go to the log and you put a record on the log to say that you start doing that. And once you did it, then you can start pulling for data from the client. Once you complete it, you're going to create a second entry in the log saying that thing was done.
Sure. Yeah, I see how that could work. That's a very large difference from how the system works today.
I'm not bringing any great design I thought of. I'm just, it's a very.
You're just grabbing existing common techniques, yeah.
Yeah.
Yes, it's
Gabby,
nothing you need new.
I've had these kinds of similar thoughts, not exactly in this case, but with other things, and it's just the weight of changing something like this is so big. And maybe once you get into it, it's not so scary. I don't know, but that's always been the thing that's kind of held me back from trying to do stuff like this. It's just such a big change.
Yeah, I agree. That's a very, very big change because it means the whole stack is going to be touched to get this thing working. I'm not saying it's a simple thing. I don't even say we could be doing that, but it's.
Yeah.
But the idea of at least having clients have to make sure that there is space on the server before sending a large write. That's something that's more easily added to the protocol. Doesn't need to touch every layer of the stack.
Is there a reason why clients like to do big writes? Because anyway, they have to split. Eventually, they have to split. So they do have the code to deal with splitting big writes. Because if they do 1 terabyte, they have to split it.
Sure.
We maybe, instead of making all the change on our side, can you tell the clients, which already have the code for splitting, don't give us anything bigger than, let's start with 1 megabyte. Well,
is it, Josh, doesn't RGW already do that? I don't think the RGW will give you huge writes.
Yeah, this comes down to really how you configure the system, and in most cases you're configuring the system to at the box it's going to use 4 megabytes for the default size for everything as the largest size that it's going to send from RGW or from RBD or from CFFS.
Okay. So 4
I mean,
megabyte is what they use, not 1. So 128 is theoretical
It's like the hard limit. Right.
Okay, but our clients don't use it because we control the clients.
Exactly.
Yeah.
Exactly.
I think the biggest concern would be if you had some user that was just writing their own custom, like, software that used librettos, right?
Yeah, and that's a more niche case. I think the QoS aspect, though, when you have multiple writers who are using very different kinds of workloads and getting very different results because of that, might be more relevant. You could have
that's
multiple
where.
XW users with like one writing very small objects, one writing very large objects, that run into this kind of situation.
Yeah.
Did we try to profile a difference between 4 megabyte, 2 megabyte, 1 megabyte, smaller? Mark, did you ever do something like this? I mean, when we set 4 megabyte as the default size for RGW, was that done after somebody concluded that gives them the best performance?
Yeah, it's not like there's best performance. There's best performance in specific situations, right? Like, say, for RBD, there are cases where you're better off with a larger size, and there are cases where you're better off with like a smaller object size, right? So I don't know that.
Allow you to write a complete object at once. If you Ceph object, a Radus object. If you're creating a new file and each time you give us 4 megabyte, it means we're going to do one-to-one mapping. We're not going to have a lot of overhead of metadata. So maybe that's why 4 megabyte came. But I'm just wondering if you do sequence of 1 megabyte, one after another, are we not going to just put them in the same space?
It's been a long time since I've looked at any of this, and it's quite possible that things have changed now. But at least back when we did this, and really 4 megabyte has been the default for a long point. It was kind of the middle of the road option at that time. Not always best, not always worst, but reasonably good in all scenarios from what we saw. That's why I remember of it anyway from when we did a bunch of the testing on it. But that 4 megabyte number even predates that testing. Josh, I don't even remember when we decided that was the default for RBD, but it was a long time ago.
I think it just happened when RBD was created. That was the size somebody picked out, and that's kind of what we ended up using for other things too.
And honestly, from when I looked at it, it was reasonable. Like, it was actually not a bad default for where it was at the time.
Yeah, I think the idea was such that it was like a reasonably large size to do a single I/O to a hard disk with, without getting too large for the buffers at the time.
The funny thing, right, is that a hard disk, even at like 512K, is reasonably good. Like, it should be able to do 512K writes, pretty well, if you're doing like full object writes. But we still saw benefit going up to 4 megabyte from what I remember. It went beyond that.
Look, I guess that might start getting into like the metadata overhead too.
So I know in iSCSI, for example, they allow you to do up to, which is again TCP protocol, similar to what we do. So I think the max unsolicited they accept is 256 kilobyte. I think it was something between, it was less than a megabyte, but more than 4 kilobyte. So maybe 128, maybe 256 kilobyte. But I don't think you even can send anything more than that amount in iSCSI. And iSCSI, again, they follow the same thing. They come with this concept of unsolicited data because iSCSI length, distance could be very long. I think, in theory, you could move iSCSI over kilometers of data. So that's why they wanted unsolicited data. I don't know that we are doing the same thing.
Gabby, I remember back when I was doing a lot with Luster, there definitely were advantages when talking directly to the block layer, to have the ability to do like writes that were like 2 megabytes to the underlying disk array. A lot of times optimizations that we did, are saying like max sectors KB to 1 megabyte or 2 megabytes or whatever the driver let us do. So at least back then on hard drives, there seemed to be advantage to being able to like be, doing big writes to the array.
I would probably I suspect that was because you compared single non-queue, not overlapping. Sorry, you didn't use multi-IO. I had this discussion long time ago. I think it's like my first post in the Linux kernel. I had this argument. Somebody said exactly this thing, and I showed him that using 2 buffers of 64 kilobyte, you could do much better than using. I think he was using 1 megabyte by just sending 2 requests, and as soon as one of them come back, you send the next one. So you're keeping a pipeline of 64 kilobyte. It will give you better performance than using one big buffer, because of this thing I discussed before. You have to wait until the buffer is full, and you don't take any action until that. So there is a big window between 2 operations. When you're doing overlapped I/O, not over if you have a queue and you send few asynchronous I/O, and there is an active queue, you don't benefit from a very big I/O. I'm sure if you'd use FIO and ask it to use 64 kilobyte and use a queue depth of 4 versus 1 megabyte in queue depth of 1, you would see that the 64 or even 16 kilobyte would be faster.
You also get the advantage of the extra memory being freed up to be used for caching other kinds of metadata for other requests too.
Yeah. And by the way, when you send big requests to the disk, you don't send them the data.
Right.
You are the one wasting your space, but you tell them 2 megabyte. You allocate a buffer on your memory space. You send a request, and then the server, the disk, is going to pull for your data. So it's doing this for you. But even this is less. It would be more efficient if you would give him 64K, because you would be taking less time to fill the data. You always have something waiting. You're going to create a pipeline. But there is never a case in which you push that much of data. The only case I'm aware of is iSCSI, because at the beginning of time, iSCSI, people thought about it about being something you write from East Coast to the West Coast over TCP. And with that kind of distance, having unsolicited data was a benefit. And I think they put, 64K, 128K. I don't know what's the number, 256, definitely not 1 megabyte. It was measured in kilobyte. I can check it. Get that we have Google today.
I think, Mark, the big portions of data, and especially last used to raise, and the thing was there that you always were looking for a full stripe write. That's why you ended up with such big IOs that being the optimum one. Just even in the raise, so the large block starts at 4 meg or 16 meg, depends on what the firmware said, and because of that, so then you go for just sequential IO and don't deal with the data, just write it straight to the disk.
That's a really good insight. Yeah, I forgot about that, but you're right, I think.
Okay, I found the definition. Yeah. Default is 64 kilobyte. You can go as high as 128 kilobyte. And that's for protocol which assume distance.
I think that might be something for the direct HD media. That to understand what the optimal or just an optimal amount of data that could be written perhaps in a single track, just with one revolution or something like this, to get the best performance for just large IOs. But yeah, anyway, for flash media, it might depend on the media.
I mean, for hard drive, right? I think historically it's what, like between 256K and 512K, where you probably see it kind of hitting that limit, somewhere in that range.
Yeah, it was changing over time a little bit depending on the sorry.
If you look at Oracle, Oracle likes to do 1 megabyte write, where they pack a lot of information and then they send you 1 megabyte. So that thing exists, but of course they cannot send you the data unsolicited. They tell you that they want to do 1 megabyte, and then you're going to poll for the data. So it's different.
Yeah.
iSCSI allow you to push the data unsolicited, but the default is 64 kilobyte, and if you negotiate and both sides agree, you could go as high as 128 kilobyte, which is
so the pure SCSI protocol doesn't load that much amount of data for single write requests. Just even so I don't remember what it is, but you have a bigger portion than the very old one, but such a big amount is not that right. So you have to split it up on the driver level already.
I mean, the pure SCSI and FCP is also like FCP is SCSI over fiber channel, which is meant to work on a very short distance, few kilometers at most, so there is no unsolicited data. iSCSI, I remember them doing that. The guy which did iSCSI used to sit next to me in the office. I think Corrito would remember him as well. So he explained to me about this, and at the time he was thinking unsolicited because he was thinking East Coast, West Coast. He thought that iSCSI is actually going to be done over just internet, which nobody is really doing, but at the time he envisioned something like this. But 128 kilobyte is the most you're allowed to send.
So what can we do? Like Josh had mentioned, the one change that potentially might not be super disruptive. Is there anything else that we can do here, or do we really need to like dig into this and look at changing the way that we handle requests?
I think we don't have an easy way to deal with this. I would suggest, if possible, to limit the max size internally from 128 megabyte to 4 megabyte, because 4 megabyte is what the client is using. But don't allow anybody to pass it. If anyway you don't expect this thing to happen, there is no benefit. And then check on the client to see if 1 megabyte, 4 megabyte, 2 megabyte, where is the sweet spot? If 4 megabyte give them some benefit, then there's nothing you can do for now. Changing the whole protocol and the whole OSD, it's a big task. I don't think anybody would do that just for this.
Yeah, I mean, I think practically we don't see 128 megabyte requests anyway. I know it's the upper limit, but Josh, I can't think of the last time I heard of anyone doing anything like that. I think it happened once or twice, but
just because I don't think it's common, I would say, to disable this, because you don't want to see some customer machine misbehaving and then eventually you find out it's something that you don't test. Because I don't see much benefit in this. Just going to stress the system. Is there any reason to keep more than 4 megabyte?
I think some folks like Mark was talking about, like that 4 megabyte was like a sweet spot at the time, but I think some folks in some systems have seen like the larger sizes, like 32 megabytes, being better for them, especially on SSDs.
There was someone I know of years ago that was doing 16. That was the biggest I think I remember hearing. But yeah.
Yeah, but that's also not using that as the IO size. Usually, that's using that as the object size. So that's a
Yeah,
bit
but it was like RBD, right? So I think they're
exactly.
saying RBD to 16, and then theoretically, if you're doing big writes, maybe you could actually start seeing 16 megabyte writes to 16 megabyte objects,
Reallocate the
right?
space, then write there. Can you do we support pre-allocation?
For RBD, we do, yeah.
So instead of doing huge IOs, just pre-allocated space and then do reasonable size IO.
Yeah.
Josh, something you said
I
earlier,
guess,
though, I think is very valid. This might be a metadata overhead thing, right? They might be seeing better performance because there's less metadata.
yeah, yeah. I think one of the reasons why we wouldn't want to do like much smaller object sizes, that's pretty clear, like with how much space a node it takes.
Yeah.
But I guess a question that keeps coming to me is that like how much of a practical difference would this make for like US purposes if we did like the prearranged buffers or processing the metadata without actually storing the data on the server side? So like a
Yeah.
majority of your
The
workload.
difference is that it would apply to a bigger change to the system in which you start doing dynamic allocation because everything is done in a preset values. So you don't need to allocate 1 megabyte, 4 megabyte. You're just going to allocate some size of buffers. I don't know, you're going to have a pool of 64K, maybe 128K, and you're just going to recycle buffers on there.
Yeah, you allocate like a space for however many requests that you're
Right.
asynchronously handling, and then you've got another little buffer that lets you pull in from that, right? Whenever data is actually being sent.
Yeah, the requests themselves should never do dynamic allocation. If you set your limit to 256 requests, you have a table of 256 entries, and it's one for one. That's, you stop doing dynamic allocation, and creation of a new task is a very quick process. But then for buffer allocation, again, you don't need to start searching. You're just going to have a pool of 64 or 128 kilobyte, and you're going to use two of them and using in double buffering to get to push the data. And you could use smaller amount of memory. If we allow big writes, and if people are doing 4 megabyte and we're doing 256K requests, each of them doing 4 megabyte, then that means 1 terabyte of memory space, 1 gigabyte of memory space just for holding the data, which in reality we could get along with 10% of that. You could cut it by 90% and you wouldn't see any performance difference. So there's going to be a memory saving cost.
Yep. Agreed.
Because when I first saw the OSD, I was surprised by how much memory I can use. At first I was really trying to pack everything, and then I realized there's so much memory. I'm not used to having so much memory. Back in Asymmetrics, there was 1 megabyte, 1 gigabyte for one director, which would be the equivalent of an OSD. Not OSD, sorry, because one director can manage 128 drives. So it would be.
Okay, so a whole host
But
worth.
everything was just keep recycling. Nobody was. You never allowed the full space. Just keep.
Yep. Yep.
Right.
So because the same thing about multitasking, it seems that we do a lot of things in parallel, but in reality we're just doing one after another. So you finish something and the resources go to the next one, and you don't hold stuff in memory for no reason. You only put the stuff in memory if you're just going to use them now.
Mm-hmm.
Josh, how horrible would it be to add like a fast, or not fast path, but like an async option to Rados? Like, I'm going to tell you I want to do this, and then let the OSD, tell you I'm ready to have data come in. It's not the primary path, but just as the secondary path.
I think it really depends on how in depth you want to go. Like what Gabby was saying about making it go all the way down to the objects layer where you're able to kind of take this in small chunks. That's really like that gets you like further towards minimizing memory and allowing you to cache a lot more of other things. And I'm not sure. I think like just adding a single like asynchronous way to like supply the data later when the OC said it's okay. That's probably not too hard. But I'm not sure how much benefit that would give us.
It seems like there's a number of things that could use it, right?
Yeah, I guess it's like whenever you have a mixed small and large object workload or high or low priority in general, where one low priority client is taking up lots of buffer space today, right?
Yeah, I was thinking about memory usage, I guess, like if we have a lot of I/O piling up, maybe then this is a case that would let us move towards that model in the worst case scenarios. But honestly, I don't know. Big writes aren't where we see memory skyrocket. It's fragmentation due to small I/O is when our memory usage really balloons. So I don't know.
Again, this model assumes that you never do memory fragmentation because everything is pre-allocated. You can just.
I know, but it's not even any of this that really makes our memory usage. It's memory fragmentation due to like a ton of O nodes being in memory at the same time that are themselves have all these dynamic structures inside them, and other H object T and everything. It's just the whole mess of it all makes things horrible.
Yeah, it's a chain reaction. So you start here and then everything
just.
Yeah, I mean, it's a completely different programming model. So I don't know if it's feasible to think about it. I don't know if just keep in mind next time we do something new, maybe that part could be designed in a different way.
Yeah, I think that's a good point. And it's kind of similar to an idea we talked about when we were starting out with Crimson as well, trying to pre-allocate all the structures needed for a request upfront, so you could do that kind of pooling and not need to do a dynamic allocation on the IO path. But doing the taking it a step further and doing incremental off the wire reads increases that memory savings even further.
Yeah.
The system I worked on, there was never a possibility of doing dynamic allocation. There is nobody was using malloc. Malloc was
right.
Yeah. And that probably would have been a good design decision like 15 years ago, right? When this was still being written at the university at Santa Cruz. But that decision early on was made, and now we have what we have.
Yeah, it's very challenging to put that switch system to work like that when it's designed the opposite way.
Yeah.
But we can certainly think about that as we like think about new things we're implementing, like the C store and maybe NVMe OF.
Yeah.
And actually, on that note, I talked to Sam about this exact topic last week, and he did mention that dynamic memory allocations are one of the things he's not really thinking about much right now. He's just trying to get correctness right, but that they are using a lot of dynamic memory. So this is an area that, maybe wouldn't be bad for someone else to come in and think about, as Sam is trying to simultaneously make sure correctness is right. Are we making are there areas where we could be doing a better job of not using dynamic memory while this is being written?
Mm-hmm.
And so you need to start with the leaf. I don't know if it's cyclic, that everything is connected to everything else, but if there are some leaf, maybe you could try there.
The root of all of it is GH object T and H object T, right? That's kind of like where, in my mind at least, that's where it all starts. You see you've got strings being used for dynamically allocated for things like object name and everything else, and then it just kind of grows from there in my mind.
But if we allow up to 256 requests, does it mean how many objects can we have open? Because every request, I assume, can have multiple objects if you're doing
Just one
snapshot
object.
and stuff.
Oh, yeah, I guess if you're talking about potentially creating snapshots, then you have metadata from like the head object as well as the snapshot. So you could say double that number.
Ideally, like in a system, you'd like to set a limit on how many requests you're allowed to accept. And then everything should derive from there, because you say every request could use that many resources, and then you pre-allocate everything. And you know how much, sorry, you do not the queue, but the in-flight object. That's why I was surprised to see that the cap is on the queue, but that's because of the unsolicited data. That's the reason for the cap. But usually what you care about is the in-flight, because everything in the queue, it's just 64 bytes. So you could afford to have 1K, 2K of them. It's really nothing. But in-flight should be a smaller number. 64, 128, I don't know.
Yeah.
And then everything else should derive, because you know how many objects you have based on how many in-flight you have. And the number should not be big. It's surprised to see that you don't need much of anything, because you use stuff, you complete, and then you recycle it immediately.
Josh, I assume there's probably some cap on metadata size when you actually figure out what the maximum object name length is and other things. I don't know that we ever explicitly figure it out anywhere, but there probably is some limit.
Yeah, there's definitely some kind of maximum you could figure out. The object names can be quite long, especially for RGW, since we end up taking those from like user input. But there's a maximum length there.
So theoretically, we could figure out a buffer size that be statically allocated to allow one object's worth of metadata to fit in.
Yeah. Okay, but a theoretical node that has
how many objects could be in flight at the same time, then you could pre-allocate the whole thing and just recycle them.
Yep.
Yeah, at the lower layer, like in Bluestar, we do have more throttling going on to control like how much data is in flight. Like there's a bytes throttle and maybe an operations throttle too. That's kind of the what's controlling capping the I/O resources from being overwhelmed. And then the queue in the OSD is what mclock is acting on, so to reprioritize within the outstanding requests. Yeah,
well, guys, go ahead, Josh.
Go ahead, Mark.
I was going to say, once you're done saying what you're going to say, I'm going to go because I want to. But
yeah, it's getting late.
Yeah. Okay. Bye.
All right. See you.
Sorry. Okay. See you later, guys. Thanks. Bye.